Hello class. Today we're going to be talking about molecular and ionic compounds. This section and the next will have tables that we're going to need to memorize. I hate to do it to you, but this is the only thing that can be done. Chemistry has some things that we just have to memorize, like sulfate and nitrate and carbonate. We need to know what these ions are. We need to know all kinds of things. But there are some tables in these two that are highly important. Okay, so we're going to define ionic and molecular compounds. Molecular also means covalent. Predict the type of compound formed from elements based on their location within the periodic table, and determine formulas for simple ionic compounds. Okay, in ordinary chemical reactions, the nucleus of each atom, and thus the identity of the elements, remains unchanged. Electrons participate in chemical reactions by being gained, lost, or shared. The gain or loss of electrons results in the formation of ions, cations or anions. This is a picture of a sodium atom. It has equal numbers of protons and electrons. Sodium is one of those that commonly forms a positive ion, a cation. And so they're showing here it shrinks a little bit, supposedly because it loses an electron. Okay, the number of electrons is 11, is uncharged. B is a sodium cation, has lost an electron, so it has one more proton than electrons, giving it an overall positive charge signified by the superscripted plus sign. The periodic table can serve as a guide for predicting the ionic charge of main group elements. Many main group elements lose enough electrons to leave them with the same number of electrons as an atom of the preceding noble gas. So group 1, that's sodium, lithium, potassium, cesium, they lose one electron to form a cation with a +1 charge. Group 2 loses 2 electrons to form a cation with a 2+ charge. Many nonmetals gain enough electrons to give them the same number of electrons as an atom with the next noble the next noble gas. Group 17 gains, which is the halogens, gain 1 electrons to form an anion with a 1- charge. This would be fluorine, chlorine, bromine, iodine, and those are the only natural ones. Group 16, which are the chalcogens, the one below oxygen, gain 2 electrons to form an anion with a 2- charge. And this would be oxygen, sulfur, and then whatever goes below that, selenium, I believe. So, next. So, for example, the group 2 that loses 2 electrons, that includes beryllium, magnesium, calcium, barium, and so on. Calcium atom loses 2 electrons, and now a calcium 2+ ion, the same number of electrons as the preceding noble gas argon. Example, bromine. Bromine atom, 35 protons, 35 electrons, gains 1 electron. Now a bromine- ion contains 35 proteins and 36 electrons, the same number of electrons as the next noble gas, krypton. Moving from left to right on the periodic table, positive charges of cations are equal to the group number. What does that mean? All right, let's escape, go there, and pull up the periodic table. So it says, moving from left to right, this group number and this group number indicate the charges that are commonly found on these ions. So this is a 1, these form a positive 1 charge. This is a 2, they form a positive 2 charge. Moving from the far right to the far left on the periodic table, negative charges of anions are equal to the number of groups moved left from the noble gas. So let's go to that periodic table here. And so these don't react with anything, but these ions, common ions, are going to be -1, -2, -3, and supposedly -4 and -5. But these chemistries get more complicated than that, so I wouldn't count on that. But these chemistries are fairly simple, and you frequently do find this in the -3 state, and this is the -2, -2, -2, and these are -1 all the way down. Okay, back to this. This method is less reliable for the transition metals, and I've told you before that the transition metals actually tend to take on more than one charge. That is, sometimes they can be in the +1 state and the +2 state in different compounds. So we'll get into that later. Copper forms the +1 state or the 2+ state. Iron forms a 2+ state and a 3+ state. Okay, made a mistake there. I got to get back into this. Boom. So this is what they were saying about the charges. These are all +1s, +2s. These are -1, -2, -3. And carbon might be seen to be a -4. Okay, now that's from the atoms of the periodic table. But now we're in the polyatomic ions. This would be like sulfate, nitrate, carbonate. Those are the oxyanions. And there are many others. The ions we have discussed so far are called monoatomic ions. That is, they are ions formed from only one atom. Polyatomic ions are electrically charged molecules, a group of bonded atoms with an overall charge. Oxyanions are polyatomic ions that contain one or more oxygen atoms. That's a subset of polyatomic ions. Okay, we need to know this chart. This needs to be memorized. I know, this is where the rubber meets the road. But this is the meat of chemistry. If you know this language, you know something about chemistry. So ammonium is NH4+. I'll tell you, ammonia, the substance is NH3, but you add an H+ to it and it becomes NH4+, and that's ammonium. Hydronium, that's actually how a hydrogen ion is found in water, is that's the hydronium ion. But it's H+ added to a water molecule. Peroxide, O2 2-. Hydroxide, OH-. Acetate, CH3COO, the way I frequently like to write it. But uncharged, it would have an H out here. It'd be CH3COOH. But when it loses an H+, it leaves this ion behind. Cyanide, Cn-. Azide, N3 minus, carbonate, CO3 2 minus. There's a typo. Let's see, escape. This is not right. It's bicarbonate, not bicarbonate. Okay? And this nomenclature is weird. The bi actually means it's got a hydrogen there. Don't ask me how that comes about. Dihydrogen phosphate, H2PO4 minus, perchlorate, etc., etc. We'll get into this later. Okay, there is a system for naming oxyions. When a nonmetal forms two oxyions, 8 is the suffix for the ion with the larger number of oxygen atoms, and ite is the suffix for the ion with a smaller number of oxygen atoms. Well, there are two common forms of this. Let's see if it's here. Yes, there's nitrate and nitrite. There's sulfate and there's sulfite. I guess they call this bisulfate instead of just hydrogen sulfate. It's also known as bisulfate. And this is bisulfite. Sulfate are salts of sulfuric acid. These are like magnesium sulfate that you can get in the drugstore. There's no problem with the body with sulfate. The hydrogen sulfate or bisulfate, this would be found in pH down as a pool chemical in Walmart. It would be sodium bisulfate. But sulfites are a little bit different. They actually trigger asthma in people. And these are used in winemaking. They've also been used to keep salads fresher. Nitrate is like sodium nitrate or potassium nitrate. One uses that in fireworks, and nitrite is used to be used in curing meats. Okay. When a nonmetal forms more than 2 oxyions, prefixes are used in addition to ate and ite. Per means it has the largest number of oxygens it can have, like perchlorate, and hypo means the smallest number of oxygens, such as in the bleach chemical. Clorox bleach is hypochlorite. I know. This is the brass tacks of chemistry. All right. When electrons are transferred, ions are formed, and an ionic bond results. Now, this would be like making sodium chloride. Ionic bonds, sodium chloride from sodium and chlorine. And the electrons are transferred from the sodium to the chlorine, and you get crystals of salt, which is the ionic bond. Ionic bonds are electrostatic forces of attraction. When electrons are shared and molecules form, a covalent bond results. I'm trying to think of carbon dioxide. When you burn carbon in oxygen, like a candle flame, you are actually forming molecules of carbon dioxide. And so the electrons are shared between the oxygen and the carbon. Compounds are classified as ionic or molecular, which also means covalent, on the basis of the bonds present in them. So, of salt and sugar on the kitchen table, salt is an ionic compound and sugar is a molecular compound. Metals readily lose electrons and form cations. Non-metals readily gain electrons and form anions. And so when you have a compound that's made from a metal and a non-metal, a transfer of electrons usually takes place and you have an ionic substance. Metals and non-metals generally form ionic compounds. So let's escape and look at this. Okay, so metals are all this stuff. Even some things down here. And these are non-metals, okay, hydrogen included. So when lithium makes a compound with fluorine or oxygen or nitrogen, you get an ionic compound. When copper reacts with oxygen, fluorine, chlorine, etc., you get an ionic compound. And the alternative that we're going to talk about is when nonmetals like carbon and oxygen, and carbon and hydrogen, and carbon and oxygen, and carbon and chlorine react, you get covalent compounds. And of course, the most common ones that we deal with are carbohydrates and organic chemistry, which deals with carbon, hydrogen, oxygen, and nitrogen. And so all the compounds made from those are molecular covalent compounds. Okay, so metals and nonmetals form ionic compounds. Examples: sodium and chlorine. When one sodium atom gives up one electron forming a sodium plus ion, one chlorine atom accepts that electron forming a chlorine minus ion, the ionic compound sodium chloride forms. Calcium and chlorine. One calcium atom gives up two electrons forming a calcium 2 plus ion, two chlorine atoms each accept one electron forming two chlorine ions. The ionic compound calcium chloride forms. Properties of ionic compounds. Typically solids with high melting points and boiling points, non-conductive in the solid form, but they could be conductive in the molten form. I take aback a little bit the idea here of electrically conductive, and that's what it means, electrically conductive. Because these are not electrically conductive in the sense of a wire, a metal, but that you can move the ions around either with an alternating current or by doing chemistry at the electrodes. But that's what it means here. Conductive in the molten form, meaning that it's composed of ions and you can move them around with alternating current. Sodium chloride melts at 801 degrees Celsius and conducts electricity, alternating current, when molten. Formulas of ionic compounds. Ionic compounds are electrically neutral overall. The formula of an ionic compound must have a ratio of ions such that the numbers of positives and negative charges are equal. These formulas are not molecular formulas. For example, aluminum 3 plus and oxygen 2 minus forms aluminum sub 2, oxygen sub 3. So you notice that the number of positive charges that come from aluminum, you got 2 aluminums with the 3 plus charge, so that's 6 positive charges. And so to balance that, you have to have 3 oxygens with a 2 minus charge to give 6 negative charges. And so overall, it has a net charge of 0, and it's aluminum sub 2, oxygen sub 3. Although pure aluminum oxide is colorless, trace amounts of iron and titanium give blue sapphire its characteristic color. Many compounds contain polyatomic ions as the cation, the anion, or both. Treat polyatomic ions as discrete units. Parentheses in a formula are used to indicate a group of atoms that behave as a unit. For example, calcium 2 plus and phosphate 3 minus forms Ca sub 3 PO sub 4 close parentheses sub 2. So the phosphate, which has a negative 3 charge, moves as a unit. And so just as we had the aluminum oxide, in which we had to balance the charges in order to come up with a formula that was electrically neutral, you have to have the subscripts here also to indicate that 3 calciums give you 6 positive charges and 2 phosphates give you 6 negative charges and yield calcium phosphate. By the way, that's what our bones are made of. Molecular compounds result when atoms share electrons. Molecular compounds exist as discrete neutral molecules, usually formed by a combination of non-metals like carbon, hydrogen, oxygen, and nitrogen. An example would be the sugar on your table, carbon dioxide in the air, water. Often exist as gases like water, low boiling point liquids, water, and low melting solids like ice. But not always. I mean, sugar does melt, but it usually reacts with oxygen and charge before it boils. Okay, that is the end of section 2.6. Thank you very much.